Yeah.
Okay, so today we have our very own Marek Liška, who will tell us about thermodynamics as a tool for quantum gravitational dynamics.
Thank you, Osman. Hi all, I'm a new postdoc here, just started in September, and I'm going to use this seminar to basically tell you the main areas of research I'm interested in, and in particular the content of my PhD thesis, which really can be summed as looking how you can use thermodynamic methods to understand better the gravitational dynamics, both on the classical level and perhaps even the quantum level, at least as far as low energy quantum gravitational corrections are concerned. This is a work I was doing with my PhD supervisor, Dr. Ana Alonso Serrano from Berlin, and also there were very important contributions from Professor Luis Garay in Madrid and Antonio Vicente Becerril also from Madrid, who I would like to mention. I'm going to start with a very brief motivation of this connection, thermodynamics and gravity, and why we should, in this case, take in the direction gravity from thermodynamics rather than perhaps the more usual one of deriving thermodynamic properties of black holes or other gravitational objects from knowing the gravitational Lagrangian. So, in this case, I'm going to focus not on thermodynamics of black holes, which is probably the area that definitely gets more recognition or probably more used to that, but on thermodynamics of locally constructed and therefore observer-dependent causal horizons. As a very simple case of this, imagine a uniformly accelerating observer. This observer, and this is well known, will see what is the inertial Minkowski vacuum as a thermal bath of particles corresponding to some temperature that turns out to be proportional to the observer's acceleration. Specifically, it's acceleration times h bar over 2 pi. And therefore, we have temperature associated with such observer, and of course, because this observer is accelerating, they will not be able to causally access the whole space-time. They will follow a hyperbola like this, some asymptotes, and these asymptotes actually form a horizon, so-called Rindle horizon. And anything beyond this horizon is inaccessible for this observer. So there is some entropy associated with this information that is inaccessible on the other side. One way to see that can be in terms of quantum entanglement, where you have some vacuum fluctuations on this side, some vacuum fluctuations on the other side of the horizon, and these will be entangled by virtue of Riesz-Leiter theorem, essentially of quantum field theory. But, of course, if you are this accelerating observer, you can only access this fluctuation and not the one on the other side. So there is loss of information, your density matrix will no longer correspond to a pure state, but to a mixed one with some entropy, and because these correlations are very strong close to the horizon, but they quickly fade off far away, this entropy will be proportional to the area of the horizon spatial cross-section with some proportionality constant eta. And this proportionality constant then can depend on details of the theory. I will get more into that later. But anyway, we have temperature. Here is en route temperature for the observer. That is h bar acceleration over 2 pi. We have entropy due to lack of information, and on top of that, if we do this, of course, standard normally Rindle wedge is something that is eternal global thing defined for eternally accelerating observers in flat spacetime. But you can construct an approximate object like that centered in any spacetime point, any regular one. And as long as you make this thing small enough so that curvature corrections can be neglected, and you also make it, on the other hand, large enough that the detector carried by the observer has enough time to thermalize and to really detect the effect. For that, the condition is that the thermalization time should be sufficiently larger than inverse acceleration. Then you can have this kind of behavior with this entropy proportional to ARA and with some unroot temperature in curved spacetime locally. And in that case, since we are in a curved spacetime, in general there will be matter present. So you will have some matter flux across the horizon, like this. And you can interpret this matter flux as a heat flux and just say, okay, I'm going to use the Clausius equilibrium relation, which tells me that if we are in thermodynamic equilibrium, or if we consider a reversible thermodynamic process, then the ratio of heat with temperature, assuming temperature stays constant, is my Clausius entropy. And right now we have entropy associated with matter fields crossing the horizon. We have entropy associated with the horizon itself. We have temperature. This behaves like a thermodynamic object. And all these definitions can be made a little more precise, which I'm afraid I won't have time to get into all the technical details of that, but as a basic idea, I hope that suffices. So this is why we can see local causal horizons as thermodynamic objects. Also notice I so far didn't say anything about gravity. This is quantum field theory, standard matter physics. So far nothing beyond it. And this, by the way, yes?
In photometric space-time, there's another two dimensions to that diagram. The area would be infinite.
Yes, that's...
So you'd be using densities there rather than actual extensive ones.
Yeah, actually, that was another thing that I wanted to say, thanks. That I used the Windler horizon as a motivation, but what I'm actually going to focus on is something finite. To avoid that, so I'm going to focus on causal elements, this kind of objects. You take a space-like geodesic ball and it's domain dependent. That's it. And then you can still imagine oscillating observers inside that will have that no effect and everything goes as before. Technically, you can just see this Windler horizon as a magnified piece of the causal element. You can see by proof on the blackboard it's the same thing. It's the same. So, okay, now we can take another step here, because if this thing is in equilibrium, then there will be a relation between this matter entropy flux and this entropy related to the ARA. This one is somehow given in terms of space-time curvature, or at least corrections to it will be if you take Riemann normal coordinates expansion of the metric. The leading order correction is in the Riemann tensor and traced over its Ricci tensor. And this one, the heat flux, is really proportional to energy momentum tensor. So if these two compensate each other, we have relation between energy momentum tensor and the Ricci tensor. And it turns out that this relation actually is enough to derive the traceless equations, the traceless Einstein equations, or in more general cases even, the traceless equations of gravitational dynamics. This was first noticed already by Jacobson in 1995, and then many authors have built on this, making it more formal, sort of smoothing over the rough points of that idea. But what we focused on as a new thing is to show that this relation, regardless of any interpretation of the nature of gravitational dynamics, already has consequences on the level of classical gravitational physics, where we argue that what we actually recover is not quite the general relativity, but something similar to it, but maybe in some cases with better or at least different properties. And secondly, we can take this further. We can say, okay, this works fine for classical dynamics and their recovery. So let's say we add some insight about what quantum gravity should tell us, what should be the status of this thermodynamic description if we go further into quantum description and see what's the impact of gravitational dynamics then. And for that we are very, very lucky, because almost all the theories of quantum gravity and also many model independent ways of computing entropy over local causal horizons agree that this term survives, and the leading order correction in 4 dimensions will be something that goes as logarithm of the area over some Planck scale area. I'm just going to put Planck squared here, it's just a constant for dimensional reasons. And this C is really the only thing that is an input from specific calculation. Its value and its sign are not dependent. But
sorry, can
yes?
you repeat, how did you argue the first term as being x?
Okay, so in this case, what I did was entanglement entropy argument. So we have vacuum fluctuations that are spatially separated but entangled. So that means if you trace over one side of the horizon, you will get from a pure density matrix a thermal one as a result.
So this is relying on quantum physics, whereas the other one is relying on classical physics.
Yes. So I'm going to briefly mention how to improve that. And also there is another thing, because there are problems with entanglement entropy when you try to use it as explanation for Bekenstein entropy of black holes. And that is what you really need here. So I'm actually, what I would really like to do is to take a little bit more basic view, and that kind of follows the original Bekenstein argument for black hole entropy. That is, we have lack of information when we are on one side of the causal horizon about the exterior. So the only part of the influenced by the exterior that we see is the horizon itself. So there should be some entropy measuring this lack of information, and it should be somehow described by the properties of the horizon.
So the bottom line is you're making a maximum entropy argument
Basically,
for the Einstein equations.
yeah.
And then the question is, what are the contributions to the entropy?
Yes. I'm going to make that a little bit more precise, also explaining this combination of classical and quantum entropy, because we can go beyond that. We can explain everything in terms of von Neumann entropies. But yeah, there are several different approaches. This really is what connects them all, these forms of entropies, and now their interpretation in some cases differs, or we can even keep it open for the time being. Anyway, for the quantum gravitational piece, the key thing is this logarithmic term is somehow universal. You get it from loop quantum gravity, from string theory, from whatever you want. So then it does make some sense to try to ask, okay, does this term tell us something about gravity? Because if it does, then it's something that does not depend on any specific method of quantizing it, or even of conceptually thinking about it. So now I'm going to the details, and for some time now I'm going to be talking only about the classical dynamics, coming back to this logarithmic terms later. And as I already said, the objects I'm going to work with are these causal diamonds. So we take a spatial geodesic ball, d minus one dimensional object, you construct its domain of dependence, and this whole thing is determined really by its center, by local direction of time that you choose, this vector n, and by geodesic length parameter here, essentially the radius of the ball in flat space-time. So it's very simple, it's closed, it has spherical symmetry, very nice to work with. In curved space-time, of course, this definition is no longer unique, there are several of them, but it is a technicality, really. We can just have this mental picture of a domain of dependence. And as I argued, these still are thermodynamic objects. They have temperature assigned to them for sufficiently fast accelerating observers moving inside. They do possess entropy proportional to horizon area, and there is matter again flowing across that gives us causal entropy. So let's move on to the conditions for a reversible thermodynamic process. First, we can compute the Clausius entropy. That's just some integration. You don't have to worry about this factor. That's just something from geometry. What's important is this piece. And I read wrong here. Here should be minus. It's a traceless part of the energy momentum tensor coupled to the local direction of time. Then the second part comes from the change in the entropy of the horizon. There we can just use right shadow equation tracking the expansion of the horizon and compute it. There will be two pieces. One is present even in flat spacetime, because when you look at the diamond, it of course expands in flat spacetime without any compensating matter flux across its boundary. So we can think of this expansion in a way like something akin to having gas in a container, opening the container and letting the gas expand. In that case, there is no heat flux corresponding to that. But
sorry, how did you get delta SC? I'm just
delta SC?
Yeah, you've got.
Okay, that's.
You've got to trace this part of the stress
yes.
energy tensor. How did you get that?
Okay, that's a bit tricky, but I can try to explain. So the idea is you need to use UNRO temperature, which is really defined only for time-like observers, of course, not for now. So what we do is this: we take a very fast oscillating observer, like this, and a class of such observers with the same assertion sweeps out some time-like hypersurface. And for this hypersurface, we can easily define the heat flux as, okay, I'm going to write this as proportionality, so I don't.
I suppose what's confusing is why it should be conformal, the stress energy tensor, because.
Okay, yeah, I'm getting to it.
Okay.
So here we have a time-like vector tangent to it, V, and here is an outer-pointing spatial normal. So this is how you would define the heat flux, or in any case energy flux. Now the problem is this thing diverges in the limit of this time-like surface becoming null, because one of these things, actually both of them, they involve in relativity affirmation. So what we can, however, do is to take delta Q over the UNRO temperature. So we have 2 pi over h bar times delta Q, and in this case, this dividing by acceleration makes this quantity finite in the limit of infinite acceleration, in which this surface moves towards the null one. So we take the limit of acceleration going to infinity, and in this limit, of course, this vector v, this velocity, it becomes a null vector, and so does the normal, because tangent and normal are both proportional to each other. So we get integral of energy momentum tensor contracted with a null vector k in both indices. Now we can write this case specifically for the causal diamond, but it's the same anywhere as a combination of the, let's say, local direction of time and the radial vector here. So we can explicitly integrate that over the angles. This first part, time part, does nothing interesting. It's just due to contraction, it gives me time component of the energy momentum tensor. And this one, we can integrate the radial unit vector over sphere to get d minus 1 times delta ij. And now when you rearrange it a little bit, you can write this as trace of the energy momentum tensor plus some t00 component, and rearranging things a little bit, you'll get d over d minus 1 times t00 plus 1 over dimension t. And that's how you get the traceless part, by integrating a null vector over a sphere.
So it's associated with infinite acceleration.
With which?
It's associated with infinite acceleration?
Yeah, with the limit. That's true. And anyway, it's associated with working with a null surface. That's really the key point. Any way you want to construct this quantity, in the end, once you integrate like this, you will get this as a result. Okay.
But if you're talking about a massive field theory that's giving rise to that stress energy, T mu nu, the traceless part of it still depends on the mass.
Yes.
So
I'm not saying this somehow forgets everything but conformal part. It's not like that. It's really all I'm saying is we get the traceless part of energy momentum tensor.
it projects onto the traceless.
Yes, exactly. So here the next point is the entropy of the horizon. It's changed, so we have this flat space-time part that we can really imagine, as I was saying before, as a expansion of gas without any heat change, something that increases entropy but is an irreversible process. So in that sense, this shouldn't be part of the Clausius relation for a reversible process because this is something extra. So we split it into two parts, the irreversible part and the reversible part that is given from Right-Shadow equation by Ricci tensor. And then integrating this reversible one related with space-time curvature, we get again traceless part of Ricci tensor and some others. Now, taking the equilibrium condition, we quickly get that the traceless part of Ricci time component is proportional to traceless part of energy momentum tensor time component. But we chose the local direction of time randomly. We can pick any vector we want to define that point. And it turns out if this condition holds out for any unit future pointing time-like vector, it holds as equality between these tensors. So now it looks almost like traceless Einstein equations. The only problem that remains is this proportionality constant for entropy. And what we can do is we can say, okay, but we still have an idea about how the Newtonian limit of these equations should look like. It must be to comply with all the experimental tests, Laplacian on the Newton potential equals 4 pi g rho. And that, when you take the limit of these equations, defines the Newtonian constant in terms of h bar and eta. Let's say. Or you can take the view that we, on the other hand, specify the necessary value of eta, depending whether you want to argue that gravity comes first or thermodynamics comes first. Matter of choice. In any case, with this identification, you will get finally the traceless Einstein equations. And now the really interesting question is how to interpret them. First of all, I'm not talking about, as Jacobson was in the original paper, gravity necessarily emerging from thermodynamics. Because Jacobson's original argument was basically this. We have gravitational dynamics identical to thermodynamics, so we should really see Einstein equations as equations of state. And then it doesn't really make sense to quantize gravity, just that it doesn't make much sense to quantize equations for propagation of sound or anything else. You can, of course, still have gravitons as a sort of quasi-particles moderating gravity, but it's really just a bookkeeping device that you would introduce, not a fundamental particle. Gravity would not be a fundamental interaction. And I think this is really too strong, because what we have to do here is to take first of all, we need to already assume that we have a curved space-time as a smooth manifold, to even draw something like a local causal horizon. Second, we need to argue that this eta is a universal constant throughout the space-time. And to do that, we actually have to assume strong equivalence principle, the form of equivalence principle valid even for bodies with non-negligible gravity or for gravitational local experiments. And that already severely constrains the type of dynamics we can get. So I think if we have to take these things, the equivalence principle, the strong version of it, and the space-time as a curved smooth manifold as input for our derivation of the equations for gravitational dynamics, we cannot really talk about emergence, not at this level. Perhaps we can make connection with some more fundamental description in terms of some basic quantum degrees of freedom of space-time, but not at this level. At this level, we are just saying thermodynamics is enough. it encodes the information necessary to recover gravitational dynamics. It's not more fundamental, not necessarily. Anyway, even in this case, there are some interesting things to know. First of all, we recovered Tracer's equation, and as a result, the cosmological constant will only appear as an integration constant in the process of solving it. We apply the Bianchi identities and everything. We get Einstein equations with some integration constant that plays the role of cosmological term. And in fact, this means that cosmological constant will be a global degree of freedom of the theory. It will be something that you need to specify in the initial value problem for it. And also, the whole derivation we considered is really only concerned with differences in entropy. It is insensitive to its base value. Whereas you know that Bekenstein entropy of a black hole that you cannot really meaningfully shift by universal constant, certainly if you compute its Volt entropy. So there is another interesting difference. And altogether, these are things that you cannot really incorporate not only in general relativity, but in any metric diffeomorphism invariant theory. Instead, what we propose is a theory called Weyl transverse gravity, or also known as unimodular gravity, which is nice in the sense that it has the same classical solution space as general relativity. So we don't lose any experimental tests of GR if we assume this to be the correct theory of gravity. What is different is the symmetry group. In this case, we do not have invariance under arbitrary diffeomorphisms, but only under the diffeomorphisms that preserve the space-time volume measure. And of course, this means that we reduce the size of our symmetry group by 1 from 10 in 4 dimensions to 9 because we have to remove the so-called longitudinal diffeomorphisms that change the space-time volume, but we instead gain invariance under Weyl rescalings of the metric, which means that we still have 10 gauge symmetries. We do not need to introduce any gauge fixing. One very important thing about these Weyl rescalings, this we really introduce as an operation acting on the metric and metric alone. It leaves matter fields completely unaffected. So it doesn't matter whether we work with conformally invariant fields or generally massive fields, anything else. Just the matter sector of the theory is unaffected by these transformations by definition. Can be done in a consistent way.
So why do you need the Weyl rescalings?
Really, what you usually means some overall function defined domain.
No, I know what you mean by that. But
Okay.
what you could have said, let's just deal with volume preserving diffeos and stop there.
With what? With
With
one?
with the volume preserving diffeos.
Yes, I could.
Or would you have included Weyl rescalings as well?
For practice, so I don't need to introduce gauge fixing because you can do what is usually done in unimodular gravity, and that is to say I fix my metric determinant to some constant, to some function, or in any case, or some constant value, doesn't really matter. And then that's it. But I can do something else. I can instead say, okay, I'm not fixing the metric determinant, I'm just saying I'm not going to use metric determinants to measure my space-time volume. Instead, what I do, I introduce a top form omega, such that it's some function times relativity tensor, and this thing I define for the time being as a background quantity. Ideally, I would want quantum gravity to give me some insight into what this is, give it some dynamics for it. I'm actually hoping to learn maybe as man what this could be in causal sets, but for now it's background quantity. And now I'm going to say, okay, so I have my metric mu, and I can use this background quantity to introduce something that I call auxiliary metric. And that is going to be, now I don't want to get it wrong, omega or square root minus g to And
There's probably one of the D.
yes. Good, like this. And now this metric has always the determinant given by m. But this is not my dynamical metric. The dynamical thing, the one that encodes information about the inhabitants, is this one. This is just a bookkeeping device I introduced. So what I really have, I have metric as my dynamical variable, and then I have this top for omega as my non-dynamical background structure, conformal structure imposed into space-time. And then this G mu, if you perform a Weyl scaling of it, it doesn't matter because it doesn't matter for this auxiliary metric that it will just inside. So that's the idea, really just to avoid setting up gauge fixing.
And are you going to tell us what the action is for Weyl transverse gravity?
Okay, I can.
Just
Yeah, it's very simple because you can construct, of course, Riemann tensor that is auxiliary with respect to this auxiliary metric.
you can.
Yes.
And so, what is this just the Weyl tensor now?
No. You go from this metric, you construct connections from compatible with it, the relativity metric connection corresponding to this metric, and then from there you take the standard definition of Riemann tensor as a commutator of derivatives. And this thing actually is the Riemann tensor in the gauge in which minus G is equal to omega. So in unimodular gauge, this auxiliary Riemann tensor coincides with the standard Riemann tensor.
Okay, and you're going to take the scalar curvature for this as your action?
Yes, exactly. And there is one important point about this action. It's going to be the scalar curvature, and obviously you are, first of all, you get here omega rather than square root of minus G. Because
but
this is space-time volume.
I should really write it in terms of G, not G tilde. So it's going to look.
This is
It's going to have
tilde.
some derivatives of G of omega as well.
Yeah, inside this.
So it's going to presumably be something like the standard Einstein coupled to a scalar can finally come to omega.
If you treated omega as something dynamical, yeah. That actually is one of the things that you can do, and it only really works if you set cosmological constant to 0, but in that case you can really construct a scalar tensor theory that is equivalent to this.
Yes.
And then different gauge fixing of this theory will either give you general relativity or Weyl transverse gravity. But this all works only when cosmological constant vanishes. When it doesn't, because it's a global degree of freedom, it really changes things, and suddenly it becomes very important that you treat this omega as non-dynamical and this scalar tensor interpretation. Which also is another point here. If you have some cosmological constant term, let's say, or if you just add a constant term here, which you are free to do, is just the lowest order Lavoc density, so in general it can be there, but now this is a completely non-dynamical term. It's lambda times omega, and then when you vary this, it's 0. Actually, there is nothing coming from this even in effective field theory. The reason for that is that if you say we compute the net current corresponding to Weyl symmetry, it's 0. So somehow this symmetry is fake, and as a result of it, there is no problem with this term even beyond the classical interpretation going to effective field theory. So this term you can add, but it doesn't matter for any physics. Actually, there is one thing that's important about it. So now we have this theory that when you vary this action and you vary with respect to the dynamical metric G mu, you will get something there are the traceless equations, traceless Einstein equations as the equations of motion. So cosmological constant is a global degree of freedom. We have seemingly perfect agreement with what we got from thermodynamics. The problem is we made some assumptions on the thermodynamic side that we do not know work in Weyl transverse gravity. So we did take a look at that, and first thing we found is that the strong equivalence principle is satisfied by Weyl transverse gravity, which in 4 dimensions singles it out together with general relativity as the only 2 theories that have this property. And second, we also assume that entropy is proportional to ara. And while the argument for this was entanglement entropy, it should also be that really the appropriate Wald entropy of black holes in Weyl transverse gravity should be proportional to ara. So that turned out to be quite technically difficult to do because we had to apply Wald entropy prescription. We ran into the problems because Wald's papers, they always impose at the beginning we have diffeomorphism invariant theory. There can be no background structure. And we actually circumvented that in 2 papers, getting a version of the covariant phase space formalism applicable to theories invariant under volume preserving diffeomorphisms and Weyl rescalings. And we found that entropy, and there is no surprise there, has the same form as in general relativity. It's ara over 4 times Planck squared. It's just, in this case, the double expression that is Weyl invariant. What is interesting is that this term that is inopposed otherwise, being a universal constant that you can add to your action, it shifts your base value of entropy. So it allows you to shift the entropy by universal constant as you can do in normal thermodynamics. Again, agreeing with the thermodynamics of space-time logic in which you have only differences in entropy as the important thing for deriving the gravitational equations. So really there is a perfect correspondence. All the assumptions we took as an input are respected by transverse gravity, and what we get as an output from thermodynamics of space-time perfectly agrees with dynamics of this theory. That's the message for the classical part. By the way, I'm not necessarily saying that this is a very strong argument against GR in general, because of course you can just say, okay, but thermodynamics is something that does not give us all the information about gravitational dynamics. So really we can say for that we need all the assumptions that I've already made, plus assumption that the energy momentum tensor is divergence free, plus assumption that the cosmological constant must be fixed to a specific value. And then you recover general relativity, but it involves a lot of assumptions that you seemingly put in by hand. So in some ways it's an aesthetic matter, but I do believe that the connection between thermodynamics and gravity is so strong that it should be at least considered. This message it gives us. Okay, this is for classical case, and now yes?
You said that the solutions of GR, all of the solutions of GR are solutions of this.
Yes.
That doesn't seem like it should be right, because I should only get one for each conformal class. Any 2 that are conformally equivalent are going to be the same here, aren't they?
Once again, sorry, I'm not sure.
Any two solutions of Einstein gravity that are related by conformal transformation will be the same in this.
No, because conformal transformation acts differently on matter fields and on gravity in this case. It leaves the matter fields untouched.
So let's take the vacuum Einstein.
Okay.
So if I take the vacuum Einstein, conformal transformations, these Weyl transformations of two solutions are equivalent.
Yes, but if you have one solution that is, you have 2 solutions of Einstein equations that are conformally related.
Yes.
Then either only one of them is vacuum because the other one needs some matter content to support it. Or if they are both vacuum, then this Weyl transformation is also a diffeomorphism. And I think in that case, Because then it's must be a transformation that doesn't change dynamics, right?
So both of them will be solutions to your big system,
I think so.
so they're not equivalent. So I can't.
I mean,
Don't think you can
either
have it both ways.
if they are both vacuum, then they are
Let's take as a solution to your system.
okay.
You're saying it's, and I can take a conformal transformation of that solution.
Yes.
They're both solutions to your system. But
Yeah.
they're not both solutions to the Einstein system. So which one do I pick?
Okay, so what I'm yeah, of course you have some redundancy there, but you have a similar redundancy on the GR side with longitudinal diffeomorphisms.
Yes.
So the point is you should always compare this solution in the unimodular gauge. That's where you can map the solutions from one another easily, because if in unimodular gauge, where we do face this gauge condition, we find some solution of Einstein equations, then exactly the same metric will also be the solution of Weyl transverse gravity.
Yes.
So for comparing the solutions, you will have to stick to this gauge, but really up to gauge freedom, physically it will be the same amount of solutions. You can map them really one-to-one, the solution space, assuming you stick to one specific value of logical constant on the Weyl transverse gravity side, then the solution space can be mapped from one side to the other one-to-one.
Yes, for instance, the easiest example to think about is the Einstein universe, which is conformally flat.
Okay.
But and it differs by the cosmological constant, which is not entering into the theory here.
Yeah, so what really happens is that here we have, let's say this would be the phase space of general relativity. So both some specific values of political constants. Then what you have here is kind of one extra dimension to it that specifies the value of lambda. So in that case, Weyl transverse gravity of course has bigger solution space by this shift choosing of the value of cosmological constant, which really only makes sense on this. But once you stay at one fixed value of cosmological constant, it's one-to-one correspondence of solution spaces. More or less. I mean, there is a small problem with that it's still a little bit difficult to give a Hamiltonian formulation of this theory. So that leaves us, but what we did was the covariant phase space at least, and in that case it looks like this. So I would say cautiously that it should be this case. Okay, now on to adding a little bit more of quantum into things, doing semi-classical dynamics. So we follow the same basic idea of thermodynamic equilibrium we did in the classical case, but now instead of having Clausius entropy flux, we instead consider matter entanglement or von Neumann entropy of matter fields inside the causal diamond. And because it's still a bit technically difficult to compute flux of this entropy for a causal diamond, or at least we didn't manage to find a reference that really does that, we instead, or actually this wasn't us, it was originally Ted Jacobson again in 2016, who considered starting from an equilibrium state of the causal diamond, which is some maximally symmetric spacetime by assumption, and taking simultaneously a small variation of both the geometry of the causal diamond and the matter fields present inside of it, the Argenian vacuum state. And in that case, you can define the change in von Neumann entropy of matter fields associated with it, and you can compute the change of entanglement entropy associated with the horizon just as a change of RF. And this, unfortunately, does not work completely in general. Here, really, it starts becoming important what sort of matter fields we consider. We do not have to limit ourselves just to conformally invariant matter fields, but we require those that has an ultraviolet fixed point. So we can view the theory locally as conformally invariant, and in that case, the entropy will still have some non-local corrections to it, but of the type that we can handle. In completely general non-conformal theory, it will become MS, because the entropy is some very complicated non-local expression and we cannot do anything. But the point here is, again, when you go through the derivation carefully, you recover traceless Einstein equations again. Sorry, here I'm missing R. I was putting this a bit in a hurry. And the one difference here is that since we get this from Feynman entropy, we have a quantum expectation value of the energy momentum tensor operator on the right hand side. So these are in fact semi-classical equations of Weyl transverse gravity coupling, classical space-time curvature with quantum expectation value. And of course, this idea again runs into some possible conflicts with the equivalence principle we took as the entering assumption. For example, in the presence of the horizon in the space-time global horizon, I mean like a black hole one, it probably becomes tricky whether you can define this expectation value of the energy momentum tensor locally correctly. Well, it's a problem that should be somehow addressed, and it should be, you should keep in mind for the following, where we go to the full, not full quantum gravity, but we entertain some additional quantum gravitational corrections. That already on the semi-classical level there are some issues that should be dealt with better going forward. And now let's go to the low energy quantum gravitation corrections. So we let into the play this logarithmic correction to horizon entropy. In this case, really the structure of the entropy is universal in 4 dimensions. It's this area term plus constant c, which is some model dependent number, times logarithm of area. This is what you get from loop quantum gravity, from string theory, from Ryu-Takaya energy formula in ADS-CFT, from replica trig entanglement entropy calculations, from phenomenology associated with generalized uncertainty principle, although there is somewhat hand-wavy, but it has the advantage that all you need there is the presence of minimum length in the theory, so in some sense it's a fairly universal thing. You can get it just by studying thermal fluctuations over the black hole horizon without assuming anything about quantum gravity really, and always it's logarithm of the area, the unimodular function. Also, this gives us further impetus to consider causal diamonds rather than Rinzel wedges, because at least in the entanglement entropy calculations you get that this entropy is proportional to the Euler characteristic of the surface, which for a plane is 0, for a sphere, as we have here, is 2, and we can get non-zero, non-trivial logarithmic corrections. Also, just purely logically here, what you would have is a logarithm of infinite area, which doesn't really make sense, and the corresponding entropy density would be non-local. But for spheres, we are more or less okay. And now I'm going to show that this leads to some corrections to gravitational dynamics. This is still very much a work in progress, but we were able to study some simplified regimes for this case. The technical challenges involved are numerous. First of all, it's the status of equivalence principle, which I mentioned. So what we instead do is to just impose the effects of equivalence principle we need. We impose that the Unruh effect survives into the quantum regime that we work with, and we impose that the entropy prescription is this one with logarithm, as we have said. We do not want anything else. We just take the pieces that we need for the time being. Then, again, as I mentioned, this logarithmic term, when you compute the corresponding entropy density, it will be 1 over area, so something non-local. You cannot write this as a local function or a Wald entropy of any modified theory of gravity. Instead, to get local dynamics, because I'm not saying fundamentally it will lead to local dynamics, but that's our starting point where we have some control over what's going on. We just tailor expand this in the changes of ARA, and in this case we do get local dynamics in the end. And we require, because it's local, for the result to be independent of the dimension size. And then there is a possibility that has been suggested in some papers that the Unruh effect survives, but it should be somehow corrected, even the Unruh temperature, which is something highly controversial. I know many experts in the field who strongly disagree with that, but in any case, this one is actually okay, because no matter what corrections to Unruh effect we consider, they end up being irrelevant to the dynamics. It's really all in the entropy. Now, first of all, just to show that this can work somehow, I'm going to say a few words about what happens when you linearize the dynamics in the Riemann tensor. In that case, after some work, and here we constrain ourselves to conformally invariant metric fields, it doesn't even work with this ones with fixed UV point. We obtain this equation that looks insanely complicated, but when you look at it, traceless part of Ricci tensor, traceless part of the expectation value of energy quantum tensor on the right hand side, and this is a traceless part of the second derivative of Weyl tensor plus this second derivative of scalar curvature, and this really are just the corrections you get in quadratic gravity when you linearize in curvature. So what we have obtained is the linearized equations of quadratic gravity with the quadratic gravity corrections kind of suppressed by Planck length squared. This should be expected because we have 1 over Planck length squared behavior of the ARA term in entropy, and the logarithmic term is O1. Yes?
When you say quadratic gravity, what do you mean? Do you mean just the Weyl tensor?
I mean, really, the gravitational theory that has this kind of terms in the action, probably something that is Weyl squared plus some.
Yeah, that's
scale,
what I
which is
thought, but I don't see any. I only see one parameter. So
yeah, it's a specific quadratic gravity with some specific relation between these two coefficients. That's true.
okay.
So yeah, you don't have two independent ones, you just have one. And by the way, it's interesting that this actually.
And what motivated the particular choice of coefficients?
That's what you get as a result when you expand the logarithmic term. These numbers.
Oh, that's what you,
yeah, these numbers are a result of the calculation of geometry. What's the only undetermined coefficient is the C, the proportionality constant, the logarithmic term. That's the only number that is model dependent. The rest follows from the geometry. And of course, there are some simplifying assumptions along the way. I'm not saying these coefficients are necessarily the right ones, but that's what you get in the model explicitly. So again, these are traceless equations, and all the argument we applied before for this being a theory invariant under Weyl transformations and transverse deformation, they still apply. This is still a generalization of Weyl transverse gravity in the same way quadratic gravity generalizes GR. And of course, when you think about it, this equation is the only thing that you can get once you linearize in the curvature tensors. You assume locality, local Lorentz symmetry, Weyl transverse invariance. The only thing that can happen is quadratic gravity.
But I could get two parameters there.
Yeah, you could. You don't.
But I don't.
Yeah, so there is some restriction beyond it. But anyway, to me, it serves as a sort of proof of concept in some way that we get something reasonable. And also the mutual sign between this Weyl tensor terms and this scalar curvature terms is the right one to avoid tachyonic instabilities. So that gave me also some hope that this might be reasonable. Okay, now we did try to go to nonlinear dynamics in a simplified setting. We had we didn't care about getting a consistent, fully general result. We just wanted to see what happens under some simplifying assumptions. And what we expected, or actually this was the very first thing we tried, so we didn't have that many expectations, but what we would probably expect is full quadratic gravity. Just we add the terms quadratic in curvature we disregarded before. But that's not what seems to be happening. Instead, we get terms, additional terms as a collection that are quadratic in the traceless Ricci tensor. And this is something that does not appear in quadratic gravity. In fact, it does not appear in any allowed diffeomorphism invariant theory in 4 dimensions. Something like this appears in 5 dimensions for causal network, not in 4D. There it's incompatible actually with the right-hand side being divergence-free energy momentum tensor. There will be, if this is a correct result, this term generically appears there in 4D, then the energy momentum tensor cannot have vanishing divergence. It will have some Planck length squared corrections to the divergence. So maybe...
Does that mean that this doesn't come from an action?
Yes. Maybe it doesn't come from a metric
From a
action.
local action, yeah.
The possibility, of course, is that this can be some disguised scalar tensor theory, something like scalar tensor Einstein-Gauss-Bonnet, let's say, in 4 dimensions. That sort of thing. That's possible. So far, we don't have the interpretation for that. We first want to do this analysis in full generality with all the corrections. This is really just one simplified setting where we were curious what happens. But anyway, there is one interesting thing about it, and that's looking at cosmological toy model for this. And we can do that quite reasonably, because when you think about additional terms that would be here beside the Ricci tensor squared, well, there will be the higher derivative terms, but those, at least the higher see here, the higher derivatives of Weyl tensor, they won't be there for cosmology because we can consider Friedman matter Bertson-Bloch. It's not there. And these derivatives of Ricci scale, again, they won't be there for conformally invariant matter fields. So for photon fluid being your source in early universe, they won't be here either. And the only other kind of terms that you expect are terms that either couple Weyl tensor to Ricci tensor, again Weyl tensor vanishes, or Weyl tensor squared. So for cosmology with photon fluid as a source, this is all there is. And in that case, we found that this model is perturbatively equivalent to effective equations of loop quantum cosmology. So you get eventually couple equations of this sort. Proportional to rho times 1 minus rho over some rho critical. Only as a perturbative result, mind you. Not like in quantum cosmology all the way to the presumable Big Bang that will be replaced by a bound. For quantum cosmology, because this then becomes 0 at rho equals rho critical, which is some Planck scale density. But still in the regime where we can consistently apply both our model and quantum cosmology, we get the same dynamics. Just as an interesting insight, of course, there is much more to be said about the physical implications of this that we haven't done yet. And now the last regime that we considered, and this I'm going to just skim through because it's new, it's a paper we are preparing right now, is going to vacuum. In that case, we can disregard any higher derivative terms because you can always rewrite them as derivatives of Ricci tensor via Bianchi identities, and the only relevant term on the right-hand side in the end will be a term quadratic in Weyl tensor. And in particular, and this is nice, we get something that is proportional to Bell-Robinson tensor as a correction, which is this tensor quadratic in Weyl. In 4D, it's a symmetric and traceless thing. It has a nice property, it satisfied an analogy of dominant energy momentum energy conditions. So this particular combination, d mu nu rho sigma contracted with a time-like vector in all indices is always non-negative. We have some non-negative source here. And it has been suggested by Jose Senovia and some people before him that the interpretation of this kind of object, of this time component of Bell-Robinson tensor is...
What is the Bell-Robinson tensor again?
Okay, it's
some contraction of Weyl
yeah,
two indices, is it?
Yeah.
Centralized.
Yes, precisely.
Okay.
It's just Weyl quadratic, so the first term is something like this, contraction into indices and 4 indices here.
Yes.
And in 4D, and then there are some other terms added to it to ensure that
it is symmetric properties.
Yeah, to make sure it's symmetric and to ensure the dominant energy condition. You can actually ask what is the most general tensor I can construct from Weyl tensor that will have all the properties, the dominant energy property, the symmetry, and everything, and you will find this as a unique solution, certainly for me. And the interpretation is that you can take this as a gravitational energy per unit area. Quasi-local gravitational energy, of course, there is no local gravitational energy, but it's can have this interpretation in the sense that, well, actually that is very close to what we do here with the causal diagrams. But there is a very old argument by Feynman that doesn't consider any horizons and just says, if you have a geodesic ball, you deform it slightly, then this deformation will be proportional to energy density. And very similarly, if you deform such a geodesic ball in vacuum, this deformation will be proportional to this thing, to time component of Bell-Robinson tensor. And in this sense, it makes sense as other than as energy density of gravity per unit area, because that's how it enters geometry of small speeds in vacuum. So it's kind of interesting, also kind of perhaps expected we get it as the right-hand side. Now, here I'm going to also use this simple case relatively to outline two things to think about this result we get in terms of its interpretation. One of them is, let's say, we want local Lorentz invariance because that's incredibly well tested. It's something that probably reasonable physical theory should have. In that case, essentially, because this thing is totally traceless, it will yield no non-trivial corrections that are consistent with local Lorentz invariance, because any meaningful correction here would depend on this vector n, which of course gives us local direction of time that is not. And then we have in vacuum just Einstein equations we recall the standard dynamics. But let's say we dare to break the Lorentz invariance a little bit, as people do in Hořava-Lifshitz gravity, or more simply in Einstein ether theories, where they introduce a time-like vector field as your local direction of time. Or in the case of Hořava-Lifshitz, introduce a preferred global foliation of the space-time. In that case, we can sort of, and take this with a grain of salt, rewrite this equation as a sort of Hamiltonian constraint. So here we have the essentially time component of Einstein tensor, written is in ADM formalism. Here is cosmological constant term. And on the right-hand side, we can do electromagnetic decomposition of the Weyl tensor. And there, when we apply this to Robinson, we will get electric component of the Weyl tensor squared plus magnetic component of the Weyl tensor squared. And this, by the way, has the same form that the Hamiltonian constraint would have in electrovacuum spacetime. The right-hand side would again be E squared plus B squared. This, of course, has nothing to do with that directly. It's just that we use the same letters to name things for Weyl tensor, but still it looks kind of suggestive. And again, it's multiplied by some Planck scale area. So the interpretation of this would be that on the right-hand side, we have some non-negative energy density per unit area times Planck scale area. and this acts as a source term for the Einstein tensor, source term that is gravitational.
So just to understand what you've done here, you've just rewritten the equation. The right hand
Yes.
side still looks like
Yes.
the Bell-Robinson contracted with
Yes.
that's what's okay. And the left hand side you just
Yes,
rewritten.
it's, and really take this just as a motivational thing that it has this nice looking interpretation as a Hamiltonian constraint. I'm not saying this is what happens, I'm definitely not saying this is exactly as in electrovacuum, it's just that I find it interesting and maybe sort of intuitive. But of course, the price to pay is breaking Lorentz invariance at Planck scale, which is something one should be very, very careful about. Okay, so that's all I wanted to say about the results we have, and just a few words about what I want to do in the future with this. First of all, we would like to do the full quantum dynamics. We would like to discuss the self-consistency, discuss the interpretational problem I mentioned with Lorentz invariance, with local energy conservation, with variational formulation, and we would like to study the physical implication of whatever we end up getting beyond the toy modular cosmological examples we have done so far. And on the semi-classical part with Weyl transverse gravity, I really want to understand better what that means. I want to get if it says something about really what quantum gravity should look like, whether we get some information about this background volume form. I want to see in more detail what the covariant phase space picture of this is, which we now have, but definitely there is more work to be done. And I want to understand what happens with this cosmological constant, the global degree of freedom, once you try to quantize this theory. Oh, that's about it. And just as a take-home message, I would say, okay, we have something about low energy quantum gravitational dynamics, which is highly speculative, and the only reason I would take this seriously is that the logarithmic correction to entropy is so universal that it's in so many different contexts that I think it's pity not to take advantage of that. But on the classical side, this emergence of Weyl transverse gravity, if you take thermodynamics as your only source of information about gravity, that is something that I consider solid already at the stage we need it. Yeah, well, that's all I wanted to say. Thanks for your attention.
So how do I know which metric I should be including in the to couple to matter?
Okay.
You've got basically two ingredients here. You've got a G nu one, you've got an omega.
Yeah, so coupling to matter is also very basically the geodesic equation has to be by with respect to this one.
It has to be the tilde one.
Yeah.
The couples to matter.
Yeah. And this one is the dynamic one. So there is this difference. Of course, the causal structure is the same for both because they differ just by a conformal factor, but yes. Coupling to matter, geodesics, everything goes by this one because that's the one that represents the Weyl invariance.
I assumed it was the other one actually. I assumed it was the G nu, which had the regular square root minus G.
I think this one is Weyl invariant. When you
But the one that I put into if I take a spinor Lagrangian,
yeah,
for instance, the electron field,
yeah,
with electromagnetism, just in there, I'm going to put in G tilde, not G.
yes, even when you do just the really scalar field, it's going to be this thing that I put the action. Definitely. Otherwise, you wouldn't get the action as Weyl invariant overall.
I don't expect it to be Weyl invariant. The action for these.
I mean, not Weyl invariant under, not conformal transformation of the scalar field. You can still do that. But just when you do Weyl scaling of the metric, that leaves the matter fields invariant. For that, you do need this action to be invariant because when you write the equations of motion, then this side is Weyl invariant by construction, right? Because it's all constructed from the metric disturbance. So if I wrote here this, without tildes, then let's say I do a Weyl transformation. Here, nothing happens. Here, I get extra factor omega to minus. And here, nothing happens. So it wouldn't be consistent under Weyl transformation. Instead, I need to do this. Actually, it doesn't matter if I do it here because I have one contravariant, one covariant, but here I definitely have to put a tilde to have the equations over Weyl invariant under Weyl transformations acting on the metric.
See, I don't expect my matter fields to be Weyl invariant.
And they are not. I mean, because we are talking, that's the key problem here. We're talking about two different things. You have conformal transformations that act on matter fields like you used to in a normal GR or normal particle physics, normal quantum field theory, and then on top of that you have these Weyl transformations of the metric, which are really something else. And these only act on the metric. So really we have two types of conformal transformations. One for metric, that is the local symmetry of the theory, and then the standard conformal transformation acting on everything as we are used to in general relativity. So for example, you can actually...
And det of G tilde is 1 always.
Sorry?
Det of G tilde is always 1.
It's always omega. Now you can set this omega any size.
Det of G tilde is 1. No, sorry, det of G
omega.
tilde is omega.
Yeah, taking the term out, this G mu cancels this one and what remains is omega. Yeah. It's a very tricky theory to build an intuition for it to be over here, to be honest. But once you get used to it a little bit, at least to me, it started to make sense after a while.
May I ask a question?
Yes?
So thank you so much for the talk. It was very interesting. You told us about why this Weyl transverse gravity is very good, but can you maybe tell us what are its challenges going ahead? Why would you, where would other theories do better than the Weyl transverse gravity?
That's a good question. So one thing, the obvious one, is that you do need a fixed background structure here, which definitely takes away part of the beauty of general relativity. You don't have complete background independence. Maybe you recover it on the level of quantum gravity by somehow getting dynamics for this omega, but for now I would say having a background volume form remains at least an aesthetic problem, if not a physical one. Luckily, this is mild enough that it does not introduce anything like a second clock effect or something like that that would lead to some experiments falsifying this theory already at this stage. It is not a problem for observational tests. Another problem that we have here, and so far I believe that's just a question of how much attention has went into this theory, is that we do not, as of yet, have a good Hamiltonian formulation, and we do not have that good an idea how to properly quantize it with cosmological constant as a global degree of freedom. This lambda being global degree of freedom, that's definitely something that is very good for the cosmological constant problem, because it means that vacuum energy does not gravitate and we avoid these possible Planck scale contributions to cosmological acceleration from vacuum energy, but on the other hand, having a global degree of freedom in the theory, once you try quantizing it, is something that will lead to problems.
Thank you.
I have a question. Hi, Marek. Nice talk. So I was wondering, so in the case you have a boundary, let's say in the standard GR, usually people add the so-called Gibbons, Hawking, York boundary terms. This to compensate, no? So do you think that, if you have a boundary also in the wild transverse gravity, you should expect something different with respect GR? A way, I'm thinking if there is really a way to distinguish GR from, wild transverse gravity, at least looking at the boundary, or, adding some different kind of boundary terms, something like that.
Very good question. My sort of gut feeling would be that you cannot use this to distinguish it, but it's something worth doing.
Okay, thanks.
I'm now confused as to what the distinction here between this and unimodular gravity is. Because if I take your G tilde as my primary field,
yeah,
then I'm going to get G tilde is G is just a unimodular gravity field.
Yes.
If I take it to be G, if I take the variable to be G over square root of G,
yes,
that's the unimodular one.
Yes. So
why isn't it just unimodular gravity?
The difference really, some people actually call this wild transverse unimodular gravity to add to confusion. So the term is tricky, but what I would say, the way I understand and the way your question understood this is unimodular gravity really relies on gauge fixing. So you set this condition. Either
I would have said no, it relies on using the field G over square root of G. G mu over square root of G to the 1 over D.
Yeah, so
that's my field.
Okay, then in that case, the difference here is that you do not consider this as your dynamical field. Then you add one thing, you add this omega as additional tensor density. So that means this is, this the right weight. This omega over square root minus G. But once we settle on that, really the only difference is that I still retain G mu as my dynamical method. This is what corresponds to gravitons. This is the respect to which I vary the gravitational action. And this one is what gives me geodesics and what capacity method. So we have this dichotomy between two methods.
But I think you then have to take omega as a dynamical field as well, if you want to take that point of view.
Not on the classical level, and you can get. There are papers studying, let's say, path integrals in this theory, things like that, going a little bit in the quantum direction, and it doesn't seem to show up as a problem, at least at the lowest orders. Actually, for this theory, in case you're really interested in details, there is a recent review, this one by Raul Carvalho, Liška, and Gerardo Garcia, that is like 40 plus pages, classical and quantum gravity, and there they really analyze this theory from all angles, discussing also modified theories of this form, discussing. There's actually a follow-up paper that discusses how this relates to string theory, and it is perfectly consistent with the way you usually get gravitational action from string theory by this beta function argument. And I think this paper really is state of the art in how far we can take things without running into big problems.
More questions? Let's thank Marek.
Thank you, Marek.
Thank you.
Bye.
Thank you.